Hello everyone. In this video, we're going to talk about BitCount question in the CSAPP data lab. As always, I copy the problem description on the left side. This question is requiring us to return the number of ones in a given integer number. Let's take the example provided by the descriptor here to see what this means. So, given integer 5 here, its binary representation is 101. So there are two twos in this number. So the result should be 2, as shown here. Given the number 7, the binary representation is 111. And then there are 3 ones in it, so the return number should be 3, as shown here, right? So how to solve this for any number? Right? Let's assume the input x is, let's just make up number in the hex format. So let's say this number is a 3, 4, 5, 6, 7, 8, 9, 8. Remember, each of these digits represents 4 bits in the hex format. So a naive way of thinking about this is we can examine each of the bit position one by one to see whether it's a 0 or 1, and then we accumulate that number into a intermediate result variable. And then once we iterate through all the 32 bits, then the result number is the final number of ones we have. Right? To write down into paper, we can have something like result equals 0, and then we do this 32 times like this. So the result should be equal to result plus x. In order to abstract the last digit of x, we just do a bit level n with number 1 here, and then in order to iterate through every bits in the 32 positions, we need to shift x to the right by 1 every time. So, and then at last, we will return the result, right? Return results. So, this should logically work here. But there's another issue is that this question only allows us to use at most 40 operations. Let's see how many operators we are using here in this solution. The real operators are this plus, this and then this redshift. So for each of the 32 times, we do 32 times 3 operations equal to 96 operations, right? This is obviously larger than 40. So we need to figure out a better way. To improve this solution, the only place we obviously need to look at is how to reduce this 32 iterations, right? We are not doing any other operation outside this 32 iterations. So this is the only place at the beginning we need to think about how to improve here. To do that, let's take a closer look at the input number and the type of operations we are doing here in their binary representations here, right? So here in the next slide, I have on the left side, I have rewritten the same input number x from the hex representation to its binary representation. I also write down the mask number here, x01, in its binary format, and then similar with the results, right? At the beginning, this bit 1 here is mapping to the last rightmost digit of rightmost bits of input x. The result is starting from 0, right? As we are doing these iterations, every time we shift the number x to the right, right? So the first iteration here, like mask and x equal to 0 here, right? Nothing changed. And then as we shift to the right side here, now we see a 1, and the result will be this previous number plus the 1 and the 1. So now we change it to 1 right here. And similarly, as we shift here, nothing changes. We shift here, then here result plus 1, then it should be 1, 0 here, right? So you can see in this way, after we gone through the entire sequence, then this result number should just get the total number of ones in the entire entire kind of sequence of bits here, right? So, okay, with that, we can see, okay, this mask is helping us just scan this entire number by 32 times here. Is there a way to do it better, right? So we can see that this entire mask right now, it only has one bit in it. What if we add one more position so that instead of abstracting one bit from this original number at once, we abstracting two, right? Instead of having only one bit here in the last step, what if we add another one here, right? So in this way, it's actually extracting two bits out of the input number at the same time, right? So initially here, the first step is since the two bits being pointed by the mask number here, both 0, so we do not change anything. But as we are moving to the right side here, now both bits are 1 actually. So here we have 1. Similarly here, so in this case it's not 1 anymore. It's 0, 0, 0, 1, 0, 0, 1, right? In this way, we're extracting two bits at the same time and then having the results here, right? And similarly, as we shift to the right here, now this time this is still 1. Here, this one is 1, and then we accumulate 1, 0. In this way, we are effectively treating the original 32 bits integer as a two 16 bits numbers, but they are basically packaged into the same 32 bits integer as a container. And then as we iterate through the number, we are processing this two 16 bits number at the same time by using a single mask here, right? At the end of the iterations, now in this time, we don't need to do 32 iterations, we only need to do 16 iterations here, right? At the end of this, we should be this result number should capture the number of ones. On the left side, we should have 7 ones captured, and then on the right side, we have 1, 2, 3, 4, 5, 6, 7, 8 here, right? So then the left side should be 8, right? And then at this point, we cannot directly return the result yet because this is a number that this result is factory are two 16 bits number packaged into the same 32 bits here, right? We need to add this left side with the right side here, right? So let's change our code a little bit here. So then this is 16 times. Already changed it to 1, so let's just say this is our mask. And then our return result before that, we need to do result. Essentially, we need to abstract the left 16 bits, shift it to the right, and then add with the right 16 bits here, right? So with that, how many iterations we are doing right now, right? So this is 16 times 3. We reduced from 32 to 16, but now we have another operation like this. So we are using 1, 2, 3, 4, basically 4 more operators. And then this is 48 plus 4, so it's 52. So now we effectively reduced the overall computing operations from 96 to 52, right? We are much closer to the target of getting below to 40 operators here, right? So that's the first step of thinking how to improve the previous solution. Now we can further generalize the approach we just took to further optimize this solution here. So what we did just now is effectively saying, hey, in order to count the 32 bits once, so once in 32 bits, in order to get this, we first do count the ones in 16 bits, and then combine the results here. Right? So what if we do even further? Let's say instead of 16 bits, we do like 8 bits first. The beauty of this is because we are able to use this one single 32 bits mask to calculate to count the ones in every 8 bits at the same time, right? So here we need to times 4, then here we need to times 2 here, right? So let me write it down here in this way. And then we can even do saying further process this by count once in every 4 bits, and then do that for the 8 segments in entire integer at the same time, right? And then at the end, we can also, one step further is we count once in every 2 bits. So what that looks like is every, in this mask, every other number, we put a 1 in it, and then we restore the number here. So here we are pointing to this 1 points to every other bits here, right? So now we only need to do shift to the right by once here, because we only need to count 2 here, right? Once we shift this and get the results, so now this result should be every 2 bits represent the number of ones in the original 2 bits of x here, right? So the left side, this should be 0. Now this one has 1, had 2 ones, so here this 2 number should be 2 here, right? Similarly for all the other things, I will just skip all this number here, right? So here, and then we need to combine every 2 bits, once in 2 bits into once in 4 bits, and then further back to once in 8 bits, and then once in 16 bits, right? And then we count once in 32 bits into combine here. Cool. So let me write it down here. Translate to the code. So now do it twice. This number should be, so what this mask should be? It's a 5, 5, 5, 5, 5, 5, 5, 5, right? And then to do this last step here, we need to do first result equal to result. We need to shift it to the right side by 2, and here I'm processing this one, right? Every 2, we want to combine every 2 bits with the next 2 bits here, so we shift to the right side, and we also need to extract the bits here, so it's a 0x33. 3 is the 1 1, right? So basically we want to apply this mask to get every 2 bits and then plus them, right? So this is a 3 3 3 3 3, yeah. Plus result, and 0x3333 here. Result, go to result, shift to the 4, and 0x. So if we want to abstract every 4 bits, it should be 0 0 1 1 1 1, right? So this every 4 bits we want to extract them should be 0f 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 here, and then results shift to the 8 bits, and so now 8 should be 0 0 0 0 1 1 1 1 1 1 1 1. Here this mask should be 0x 0 0 ff 0 0 ff, and the last step we need to shift to the right side here. So with this, how many operations we are doing here, right? So we are doing 2 times 3 plus, so area of this merging or this combining step, we are taking 1 2 3 4 4, so 4 times, now we are doing 1 2 3 4. So this is 6 plus 16, so it's 22, right? So now if we are able to do this, then the total number of operators is 22. It's already way below the threshold of floating. Before we go to the coding part, there are 2 observations I want to call out here. First one here is this overall cost has 2 components, right? the first component is the coming from this original previously it was 32 iterations, right? So, but we decrease it from a 32 to really 2 times into 2 here. And what effectively we've done is that we improve this part by 16 times here. And then the second part is the second component of overall cost is this part is introduced by the overall combination steps at the end, right? This 4 is really the saving we got from reducing removing the 16 removing the kind of 30 loops here, or improving the 32 iterations by 16 here, right? This is really about the square root 16 here. This 16 is the factor of improvements we did here. So we can say that we actually improved one component exponentially, and decrease the other one linearly. Cool. The second opposition is even though we say overall, now we say the compute time is 22 operators, but in practice, when we do the coding, since the bits.c source code has a requirement that we can now use a integer constant greater than 0xff, we will need a few more operations than 22 in order to generate masks like this, which are larger than allowed 0xff here, right? Okay, with these two observations, we can move on to the coding part. Okay, to make it easier for us to cross-reference the pseudocode when we are programming here, I copy the same content for pseudocode from the previous slides to this text file on the left side. Now let's start coding here, right? So first we need a variable called result. We also need a mask. The first mask we're gonna use is this one, and then this mask will need to further process. So now this mask should be something like this 0101 01 here. And then the first time we need to assign result equal to, and then we do the x shift by 1, and then x result equal to, right? This couple of lines corresponding to these 2 times. This time there is the mask we need to generate is this all the 3 here. So, and then mask equal to, so now mask equal to 0x3333. And now we do this result equal to, and then now we are done with this, and now we need to update the mask to be this number. So mask equal to, now this is 0f, 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 0f. Now we need to do 4 here, right? And then next one is 00ff. Last step, now the mask at this point it should be ff. And then at last we need to return result here. Okay, let me try to compile this make b test. Okay, we actually see 2 unusual warning here. The first one, we forgot to assign the redshift value back to x here. This is a good catch. Let me fix this one. The second one here is complaining that we need to guarantee the right order of operation here. Cool. So okay, let me save this. Let me recompile again. Okay, now everything is fine. Let me test this. btest-f BitCount. Okay, we pass all the tests and test cases here. Let's see also how many operators we are used. DLC-e bits c here. In this BitCount, we are using so remember earlier on we were saying even though we were projecting to use only 22 operators, but since we need to do all the operations in order to dynamically generate all the masks here, so it will take a lot more than 22 here. In the end, we are using 36 operators, still below 40. So we have solved this problem now. Okay, with that, I will see you in the next video.
Thirty-six operations.